thanks. It's great to be here. It's been a lot of fun today, talking with so many different people and learning about the various different things that people are doing here. Yeah, it's just been great, so I really appreciate it. So I hope that I can teach you a little bit about some of the things that we're doing at Emory, in particular some of the things that I'm doing. So let me just mention this work that I'm going to talk about is joint work with a variety of different people. Julianne and Piotr are former PhD students of mine. Veronica and Ching are current PhD students. Stuart is professor in the Department of Physics in the Institute for Astronomy at the University of Hawaii. These other folks are all in the Department of Radiology at Emory. And so most of the work I'll be talking about, mostly the radiology stuff. I'll just mention briefly a little bit some of the work that I've done with Stuart. Okay, so let me just begin slowly. There's a lot of words in my title, probably too many words for a title, but that's what I did. So let me just say, in the title, there's this word called inverse problem. So I know there's lots of experts here in inverse problems, but let me just mention briefly what an inverse problem is. Well, actually, it's hard to say exactly. It's hard to define precisely. But usually you think of it paired with a forward problem. So for example, given two numbers, I can multiply them together and get the number z. An inverse problem, there's several inverse problems associated with this. Given the multiplication, given 86, what two numbers multiply that give me 86? Of course, that's a hard problem to solve, in fact impossible unless you put some constraints on it. In general, you might think about a forward problem as being something that's sort of well-defined, a well-defined process. So you're given, in some sense, an input or a cause. It goes into a process. You can think of f as a function, and out comes f of x, something like that. So an inverse problem associated with that would be, well, given the output of this function and the function itself, what input was in there? So that's an inverse problem. Another inverse problem associated with that might be you don't know what's going on in this box, what that function is. So you might bombard it with some signals and measure the output and then try to determine what's going on inside the box. So that's basically what we mean by an inverse problem. In applications, I might think about it in the following way. Some of the applications we've been working on, one of them is atmospheric imaging of space objects using ground-based telescopes. And typically what happens is any light that comes through to a telescope that's on the ground has to pass through the atmosphere. So there's some atmospheric layers that it has to pass through. And the wavefront originates as a single plane wave. And as it hits the atmosphere, it gets distorted. And that plane wave is no longer a plane. Okay, so what happens is that the light that reflected off of objects in space then is imaged in the telescope as distortion. Now, you may say, okay, well, those images, that looks a lot worse than anything that I've seen NASA publish in their documents and stuff, and that's true. On the other hand, NASA's post-processing a lot of the images that they may show, and when you image during the night, on a clear night, you might get much better looking pictures. On the other hand, the Air Force in particular, the United States Air Force, is interested in imaging objects in space not only at night when it's a perfectly clear night, but also during the day. They also might want to look at the horizon when there's objects that may not be perfectly straight above where they're at. And in those poor seeing conditions, you can get really, really awful looking images. And the idea is, of course, given this image that you observe, and then you have to know something about how that wavefront was distorted as it came through the atmosphere, can you recover, the inverse problem is to recover then what the object, the original object was. Another application that we've worked on with some folks in radiology at Emory is positron emission tomography, where brain imaging. So the patient is put into this scanner here that you can see over here. And they have to go into the scanner for a long time. Usually positron emission tomography, they go in for about 30 minutes. And they collect data during that time. And during that time, they ask the patient not to move. Please don't move. And of course, that's an impossible thing to do unless they strap you down. But of course, you might get claustrophobic doing that. And so you scratch your leg or whatever, and you move a little bit. And you end up getting images that are slightly, maybe slightly blurred, because you're moving during the scan time. Now that you may be a cooperative patient and not move very much, but there may be cases where they want to image patients who are uncooperative, people with mental illnesses and things like that, and the distortion might look much worse. So the inverse problem is given this distorted image and something about how the head, information about how the head was moving during the time, and I'll talk about this later in the talk, can we recover a better looking image. The other application I want to mention is something that we've been working on in breast imaging. So a standard breast cancer screening thing would be to use mammography. Everybody knows what mammography is. It's just an X-ray. So the breast is put into this, in between these two plates and compressed, and then a single X-ray image is taken. And this is what an X-ray image might look like. The image looks a lot better on my screen, by the way, Eldad, than it does up there. Anyway, so it does really. Anyway, so but anyway, it doesn't look that good. It's a single X-ray image, and it's hard to get a lot of diagnostic information about whether a tumor or something small is in the middle of the breast. It might not be seen with the X-rays adding up one on top of each other at the detector. So the technique that actually in the United States which was just approved by the Food and Drug Administration in last winter is a technique called tomosynthesis, which is a limited angle tomography technique. And so what you do is you use the standard X-ray mammography machine, but you allow the X-ray source, this is the X-ray source, you allow it to move. So I'll move it from plus or minus maybe 30 degrees and move it in increments of say 1 degree. And each time I move it, I take another X-ray image. So I get several X-ray images. And from those X-ray images, those several that I collect, I want to then reconstruct pseudo 3D reconstruction of the breast. So when you do that, I tried to show this here. So what I'm going to do is I'm actually going to scan through some of these things and see if something comes up. Maybe this one looks a little bit better. But okay, so I'm going through the slices, and as you see, you can see this little white dot here, which didn't show up in the original mammography scan, so you don't see it there. Excuse me. But as I scan through these sort of slices of the reconstruction, you start to see this little white thing show up. And it's not an anomaly in the data. It's actually something in the breast that you wouldn't have seen in a particular single mammography scan. Now that little dot isn't a big deal. It's a microcalcification. It's not a tumor or anything that's affecting the patient. But it is interesting to see that you can see this in these things. Okay, so the inverse problem here is given all of these projection images, can you then reconstruct this three-dimensional object? Okay, so those are some just sort of motivation of what an inverse problem is and what we want to do, some applications of what we want to try to solve. So I want to, for the rest of the talk, give a little bit of mathematics and algorithms that we're using to solve these things. So I'll talk a little bit about the mathematical model. I want to tell you a little bit about some of the challenges that you need to face when you try to write algorithms for these things. In the linear case, it's a lot easier to understand. And again, there's several people here that are quite expert at this kind of stuff, as well as at solving nonlinear inverse problems. Nonlinear are a bit harder. So we'll talk about that a little bit, and then and sort of talk about a couple of applications related to these things. All right, so we need a little bit of mathematical setup. As I said, we think of a forward model as given some data and a function. I evaluate the function at that data. This stuff is noise, and I get some measurements out. Okay, so but typically in an inverse problem, you're given the data and the function. Maybe some statistical information about the noise, and the idea is to figure out what the object was, or what information about the object that you're looking for can you reconstruct. Okay, so some examples of what this function might look like. It might be quite simple, right? So I might think of it as just a matrix vector multiplication. So we'll have b equals a times x plus some noise. Okay, so that would be a simple linear inverse problem. We'll talk more about that in a little bit. I might have a situation where I don't know, well, let me write it down like this. I have a matrix times a vector again, so a vector that's my object, something about my object. but I don't know the matrix A exactly. I have some model parameters that need to be defined first to get the matrix, and then I have a linear inverse problem after that. And so I have this sort of mixture of linear and nonlinear stuff going on. Or I just might have some complicated function that is harder to write down except in specific application situations. So I might have something quite complicated there. All right, so let me go back to these applications that I showed in the beginning and what the inverse problems are. Again, I have this, I'm observing data. This is my observed image. And I want to know the inverse problem is to figure out what the object is. And along the way, I need to know how that atmosphere is distorting the wavefront as it comes through. So I need to, that's part of the inverse problem in some sense. Okay, so the inverse problem actually involves actually two parts to it. One is to figure out what caused the distortion. What is that wavefront distortion as it comes through the atmosphere? I need to understand that first so that I can get the object. So X is going to be my object that I'm looking for, the picture of the true object. And this W is the wavefront. And the W will define a matrix, a convolution matrix if you like. And I want to find both of those things. So I have sort of two inverse problems going on. In the these ground-based telescope applications, the telescope has a sensor that not only collects the image, but it also can be used to collect gradients of the wavefront. So the wavefront comes through, and if I have the gradients information from it, then I can reconstruct the wavefront from the gradients. So this would be like a Laplacian operator, if you like, something like that. And I reconstruct the wavefront, and then after I get the wavefront, then I have this other linear inverse problem, and then I solve for that. Of course, they're coupled, and I might say, well, I might not know the wavefront exactly, and so I might want to do a sort of joint nonlinear optimization on X and W there, for example. Anyway, so those are the inverse problems associated with that. This application is quite similar, right? It's an image blurring problem again. And what you do in this case, or what we're doing in this case, is that we attach to the patients, well, we don't, the people in radiology do, they attach sort of a cap to the patient's head that has little markers on it. And then outside the machine on the other side, somewhere over here, there's a high-speed motion detection camera that like about 20 hertz, calculates or records the position of the head. And then from that, you build up, let me say right here, you get the position of the head at like 20 hertz. From that, you can build up this, this motion blurring matrix, and then you solve the inverse problem for the object. And this is a 3D imaging application. I'm going to talk more about this, how I get the matrix, or how we get the matrix later in the talk. In the breast imaging, this is a lot harder, actually, in some sense, or it could be a lot harder, depending on several things. As I mentioned before, the data that you collect, this B is a bunch of X-ray images at each angle as the source moves. The function F then is going to be defined by, okay, how accurately do you want to model the device characteristics and the physics of the X-ray imaging device? And I want to talk a little bit more about that later. But in any case, this function can be either quite simple, very linear, or it could be quite nonlinear. All right, so once I get this inverse problem, one of the things that you need to know about inverse problems is that typically they're also ill-posed. Ill-posed means that typically if I have any noise in the data, it can amplify errors in the computed solution. That's the basic idea of what it is. And so trying to given this noise-corrupted data and the function f, trying to figure out what this exact thing is quite difficult to do. And in fact, generally impossible. So typically what you do, since it's so sensitive to amplification of noise errors, is typically what you do is you incorporate something called regularization. And in regularization, you try to overcome that stability by replacing the hard problem by one that is a politician way to do it. You can't solve the problem that someone posed to you, so you change the problem to one that you can solve. And hopefully that problem's not so far away and it's a little bit easier to solve. And there's lots of books written on solving ill-posed inverse problems if you're interested in that kind of thing. And then, as I said, there's in this audience lots of experts on these kinds of problems. All right, so let's try to talk a little bit about the challenges of solving these ill-posed inverse problems. And I will look at the linear case because that's the easiest to understand. So in the linear case, I'm going to assume that this matrix A is known exactly, and I measure noisy data. And so what we're going to do is just do a simple sort of thing. I'm going to take the matrix and I'm going to compute its singular value decomposition. So U and V are orthogonal matrices and sigma is a diagonal matrix. And so what can I do here? Well, I can expand, if I say, okay, let's just say for a second this noise is small, forget about it, and apply A inverse to both sides of that equation. So A inverse times B, and expand it out in terms of the singular vectors, the columns of U and the columns of V, and the singular values, the diagonal entries on this thing. So if I write it out in terms of a sum of outer products, this is what it looks like. Now, if I expand it all out, what you see here really is that you have in this solution here, sort of ignoring the fact that I have this noise here, you get the exact solution here, the thing that you really want, plus some error stuff. And yeah, so actually what I would like to do, and I know a lot of you will be bored with this because you've seen it before, but let me just show you some little demos, right? So I have a couple of little MATLAB stuff that I want to do just to try to illustrate some things. So I'm just going to write a simple 1D. So I know I'm talking about images, but let me just use a sort of a one-dimensional imaging example for a second. So on the left here is my sort of true object, if you like, and on the right is my observation. Okay, so and I didn't add any noise to it. So what I could do is then just compute A inverse B, right? A backslash B. And let me plot the solution that I get on top of the red thing and see if I get it exactly. And if I do, you can see, I don't know if you can see it, but it is exactly on top of it, right? So I did quite good there. And that's, okay, so that's fine. I just did that in MATLAB. Now, let me do this. Let me take, oh, shoot. 1 second. I didn't know it was going to go off the thing there. We changed the resolution on the computer, so let me mix this up a little bit. Okay, so you can see that. Okay, so see the difference between the middle one, which has no noise in it, and the right-hand side, which has a little bit of noise added to it. And if I do the same thing now, I apply A inverse to this thing on the right-hand side, this right-hand blurred one, noisy one, and I compute A inverse B, I get, it looks better on my screen, by the way. Actually, it doesn't, right? So what's happening here is the solution is oscillating up and down, and it's going off the screen, and it's not matching the red anywhere. I don't know if you can see the red in there or not, so it's not doing it at all. Okay, so the idea is what's going on there, right? So let me just, let's investigate it. So we talked about the singular value decomposition, so let's compute the SVD of this matrix and see what it gives us. I know I haven't told you what the matrix is, but it's a matrix. Okay, so let me compute the singular values. So if I plot the singular values, they start off about 1, 10 to the 0, and they decay down to, I don't know, 10 to the minus 10, something like that. So they get quite small there, right? So the matrix is ill-conditioned. There's not a gap in there to say, okay, the rank is 100 or something like that. It just, they decay to 0. Okay, that's typical of these kinds of problems. The other thing that's typical is, let me plot the singular vectors. So I have this matrix, this SVD U sigma V transpose. Let me plot the singular vectors, the V vectors. So I plot the first one, and that's the one associated, so this vector here is associated with the largest singular value up here. And let me plot the second singular vector. So this one right here is associated with the second singular value, and so forth and so on. I'll plot the third one, the fourth one, the fifth one, and so forth and so on. So what do you see? You start to see a little bit more oscillation in each of these things, and now I keep plotting them, and the oscillation keeps growing. Right? So the amplitude doesn't grow, but the amount of oscillation does. And that oscillation is the thing that's getting magnified in the solution. That's what you're seeing here with this, all this blue stuff on the screen. Okay, so again, what we're seeing here is when I compute this error stuff here, I have the truth here, whatever that truth is being dominated by the error. These vectors here oscillate a lot, especially corresponding to small singular values. So if I divide by a small singular value, it magnifies this noise component, magnifies the oscillation, and that's what you see in the blue. Okay, so that's the difficulty with something like this. And this is not, this is this is very well known. And so what you do is, so I just said this stuff here, right? So you get these things going to 0, they oscillate, and you get some trouble. Okay, so what do? Well, you say, well, if it's these small guys that are causing me trouble, let's filter them out. So that's one approach that you might use. So you say, okay, well, let me put in these extra terms here. If these were all 1, I would have the inverse solution that it gave me garbage. So let me put these guys in here, and these will be filters. And I'll say, okay, allow the large singular components to come through because it gives me information about the signal that I want. But don't let the small singular values come through because they're causing the noise amplification. So there's lots of ways one can imagine doing these things. You can simply just truncate, pick which singular values you think are good, and then throw the rest out, right? So a truncated SVD type thing. Or you can have a smoother filter, right? So this is a Tikhonov type filter. So this is a parameter I need to choose. And if I look at these guys, well, and this is going to be a small number in here. So if this is 1 over 1 plus 0, I get something like 1. On the other hand, if this is close to 0, I get 0 over something that's not 0. So I get something that's close to 0. So that does what I want. And you have other ways to do it as well. Okay, so there's lots of options to choosing these filters. All right. On the other hand, these problems that we're interested in are large scale. So if you know anything about the singular value decomposition, it's really difficult to compute an SVD of a general matrix that's very large. You can try it in MATLAB, do SVD of a rand of something that's big. So there are other ways, of course, to incorporate regularization. Another way is to use a variational form where you have a data fit term plus some dampening term, if you like. And so you have to choose this thing, and this sort of what you want to dampen, and then how much you want to dampen it. So typical Tikhonov regularization, which I talked about before, in terms of the SVD, can also be formulated in this way as well. And I can choose L to be an identity matrix. I can choose it to be a differentiation operator or something like that. I can use total variation or sparsity. And I'm looking forward to seeing more comparisons of these things in the future. In any case, I'm going to think about Tikhonov regularization mostly for the rest of this talk. And actually, I'm mostly going to use this L to be the identity matrix. And let's just solve that problem that I had before so you can see what happens when I do that. So again, I know that this may be trivial for some of you, but let me just do it anyways, just to see the difference. Okay, so again, the truth is the red, the middle is the noise-free observation, the right is the noisy observation, which is something that would be most realistic. If I take this alpha, I had the Tikhonov parameter up there to be 0, it gives me this inverse solution, exactly A / B. If I increase my alpha parameter and I solve it, I can actually do that in MATLAB in this one just by using \. If I form this overdetermined least squares problem, you see the oscillation has gone down a bit. It's not great, but it's gone down. So maybe I'll increase the alpha a bit. And the oscillation's still there, but at least it's starting to match the solution a little bit, the truth, right? Reducing it or increasing alpha a little bit more, I actually reduce it quite a bit. Now, I've lost a little bit of amplitude here, so I haven't done perfectly. So let's just increase alpha a little bit more. Maybe we can even do better. On the other hand, if I increase it too much, I over-smooth the solution, so I don't get something that's very good. Okay, so I'll go back to what I had before, and that looks good. So I have to figure out what this alpha is, and that's a hard thing to do, especially for large-scale problems. Okay, so that's just to give you an idea of how this regularization can work. Now, I'm never going to get the truth back. It's impossible to do that, of course, but my goal is to try to get as close as possible. Okay, so right, so that was, I used this filtering. I talked about filtering. I talked about this sort of variational regularization. Another approach is to use sort of basic iterative regularization, where you would just apply an iterative method to the data fit term, and don't worry about adding any dampening term or anything like that, and run your iterative method on it. If you run it to sort of convergence, it will converge to what you expect, the inverse solution, A inverse times B. And that, of course, is not very good because it's my truth plus this error, when the error is usually swamping things out. Typically what happens in these problems is that you get something called semi-convergence, which means that at the early iterations you start to see the solution come, but then all of a sudden the noise starts coming in and you start to see it get worse. And there's lots of iterative methods that behave like this. And I won't go into the analysis, but maybe I can just show you an example of this real quick, so you can see it in action. So here's, I'm just going to use, okay, what is Lsqr? It's a conjugate gradient type method that can be used to solve a least squares problem. So that's all Lsqr is. It's an iterative method. So what I'm going to do here is I'm going to, on the, again, oops, I started it up. What am I plotting there? I'm plotting the solution at each iteration. And yeah. I don't know if you watched it. Did you watch it? Okay, let me do it again. Okay, so if you watch it, I'm going to plot on top of the red the solution at each iteration. Okay, and at the top I'm going to tell you what iteration it is. Okay, so if I start it up again, you see it? There's the solution, and I keep iterating, and the solution starts to get worse and worse. Okay, so you saw that if I had stopped the iteration at the right point, I probably would have had a good solution, but I didn't stop. I kept on going. All right, so that's what I get from there. Okay, so, right. So why does that happen? I want to talk a little bit about that because it's going to help us figure out how to, an approach to try to stop the badness from happening during the iteration. So I'm going to talk about Lsqr. Lsqr is based on something called Lanczos or Golub-Kahan bidiagonalization. This is something you would see in a numerical linear algebra course. Basically, the idea is you start an iteration and you start building up a set of basis vectors. There's W's and Y's. You want to build up a set of basis vectors and a bidiagonal matrix at each iteration. And that everything is going to just grow bigger and bigger. So I'm going to get more and more columns from my W matrix, more and more columns from my Y matrix. And my bidiagonal matrix, these two diagonals here, the rest are zeros in the matrix, will get bigger and bigger as the iteration grows. So at the 10th iteration, I have an 11 by 10 matrix here, for example. Okay, so that's what we do. And then in Lsqr, basically, what you do is instead of at each iteration solving the whole least squares problem, you project it down to a smaller subspace. So this matrix may be huge, but when I project it down to this bidiagonal matrix at each iteration, this is a small problem to solve, right? So B is a matrix size that depends on the iteration. At the 10th iteration, I'm of an 11 by 10 matrix. Very simple problem to solve, and I do that. Okay, so that's what we do. Now the interesting thing about what the properties of this method are is that this bidiagonal matrix is very similar to the matrix A in the sense that the large singular values of the matrix B approximate well the large singular values of the matrix A. This is a property. Oh, actually I showed it here. So I used this matrix that I had shown with my MATLAB codes. So what I've done here is I've taken the matrix A. It's small enough in this particular little example to compute all its singular values. And then I started the bidiagonalization. So I guess I'm at iteration 10 here. I don't know if you can read this, but iteration 10, I've plotted in red the singular values of the original matrix. And in blue, I've plotted the singular values of the bidiagonal matrix. So you can't distinguish the red from the blue here until you get down to this one right here. So the large singular values of B and A match each other well. As the iteration proceeds, this is just a plot of the difference between these two, because I don't know if just showing them one on top of each other is a little deceiving. This is 10 to the minus 10 here, difference between the large guys, and then as the first 5 or so, and then they of course start to separate a little bit. As the iteration proceeds, again, I get the large ones matching well, and the smaller ones maybe not matching so well. And again, this property just continues. So that's a property of the algorithm. So what it means is that, as again, you can see that at the early iterations, I'm getting the B matrix gives me the large singular components. Those are the ones that I want to reconstruct. So I get those things, and so if I stop the iteration early enough, I've solved the problem on a subspace that corresponds to these large things, which is really what I want to do. That's what all filtering, the filtering discussion told us. So I'll stop it, before I converge. Of course, I'm going to converge to the inverse solution if I run it too long. So let me just show this again. So what I'm going to do is show, okay, so there I am. I stopped at the 7th iteration, which is pretty good. If I stop at the 20th, maybe you like that one better. Maybe you like the 7th one. I don't know. If I continue to iterate, though, I get worse. Now, this actually brings up a good question, right? How do you know when to stop the iteration? Now, you might say, well, let's look at the residual, because that's really the only thing I can look at, b minus ax. And if I look at the residual, what you see is that the residual, if I plot it, decays, and, well, it starts to flatten out. And I might say, well, let's stop when it flattens out. So where is flattening out in this case? Is it at 7? Is it at, I don't know. I mean, it's hard to tell in some cases. Okay, so this is a hard question of when to stop the iteration. So there are ways to do it. If you can measure if you know an estimate of the noise, you can use something called discrepancy principle to guide you in when to stop. What I want to talk about next is, if I'm wrong about when to stop, can I avoid this additional oscillation from coming into the solution? Okay, so what we're going to do is use something that's called a hybrid method. Now, hybrid methods have been around for a number of years and been investigated by a lot of people. What I'm going to talk about is some work that I did with Julianne, which is a former PhD student, and Diane O'Leary, and the code that we used developed for this. So again, the idea is in the bidiagonalization, you project down to a small subproblem, and then you solve it on this small subproblem. So what we're going to do instead, before we didn't put any regularization in, but let's add some regularization to it. And on this small problem, let's hit it with some sophisticated methods. It's small enough that I can try some sophisticated parameter choice methods. I didn't mention any of these things in the talk, but there are ways to sort of estimate what this alpha should be given the data. Okay, so we'll hit it with something quite sophisticated on this small problem at each iteration. Okay, so that's what I'm saying here. I'm going to use some sophisticated parameter choice method and hopefully avoid this oscillation from creeping in if I stop too late accidentally. Okay, so that's what we're going to do. Now, the way we're going to do it is we're going to use something called generalized cross-validation. Actually, we use a modification of it's a weighted generalized cross-validation method. I don't have time to tell you exactly what that is, but it's a scheme to do that, and we're going to try to figure out when to stop the iteration. So let me just show you this on the toy problem so you can see what it looks like. And I want to go back to realistic problems in a minute, but let me just show you the toy problem. So here it is. This is our code, right? So it's this is basically how you call it. You just give it a matrix A and a vector B, or a object matrix. It's not really, it doesn't necessarily have to be a double matrix. It could be a structure or something like that. Anyway, you just call it like this, and it tries to figure out when to stop. In this case, it decided to stop at iteration 9. It said, okay, I think that's the best solution. Now, you can tweak the tolerance on it. You can say, okay, we have this, like the optimization toolbox. We can change the options to it, and we can, change when we want to stop. Tune down the tolerances so that it's a bit more strict, and run it even more, and it will decide to stop later. In this case, it's decided to stop at 50 iterations, but still, last time, without this additional regularization at each iteration, I got a lot of oscillation in it. Okay, so and this time we didn't. So that was that's quite a nice behavior. Now, I'm not claiming that this method is going to work for every single ill-posed inverse problem in the world. That's not. If anybody claims that, they're wrong, right? I mean, that's not possible. But it does work well on a wide class of problems, and I'll show a more realistic one in a minute. In fact, let me explain a more realistic problem. So this is this positron emission tomography example. Again, it's a person who goes into a positron emission tomography scanner. If you don't know what that is, it's a nuclear imaging technique where you're injected or you ingest a radioactive substance. You put it into the machine and you glow. And the machine measures your glowing. And then you can't cross the border for a while because you'll be stopped by the border Homeland Security guys and they'll say, radioactive. Okay, so you have to wait until your radiation goes down. Anyway, you and then they say, don't move, and of course you move. So they attach, as I mentioned before, a cap with some markers on it. And then they use a motion detection camera to measure your position several times a second, about 20 hertz. And from that, we can construct a large matrix. I'll tell you what this matrix is in a minute. And then you solve this inverse problem, okay, from the position information. Okay, so let me tell you how we get this matrix. We assume the position at a bunch of time frames is known. From that, we can construct a matrix A. This A sub L at time L says how does the object move from one place to another place. If you like, you can think of it as interpolation. Move the object and interpolate. It's a lot like what you do in registration. And so you construct these matrices. The blurred image, you can imagine what blurring is like if you open your camera shutter and you leave it open for a long time and an object moves across it. You can imagine that's equivalent to stopping that object at a whole bunch of time sequences and then adding them up, adding them as a sort of an averaged thing. So that's the way we're going to model it. So it's sort of an average weighted sum of the object at a whole bunch of different positions, and then there's some noise added in. So this matrix here, you construct from the position information. Each of these these matrices A sub L are sparse. The sparsity pattern may or may not match each other. Most likely they won't. And so the more matrices I add up here, the less sparse the matrix becomes. Okay, so that's an issue. All right, so let me just show you, this is a made-up example. This is one of the most famous characters in the United States. Anyway, so again, I made it up. What I did is I randomly shook Homer's head, and I reconstructed. So this one is just a little bit of blurry. I don't know if you can see it's a little bit blurred compared to the truth. Oh, no, actually, this is the reconstruction, I guess. This is the regularization parameters that the method is. So this method computes this regularization parameter in each iteration. And you see that it tries to figure it out at each iteration, and eventually it figures it out and sort of flattens out and says, I think I know what the regularization parameter is, and it reconstructs the image here. This is a little bit more blurred, and again, it figures out the regularization parameter and flattens out, and a little bit even more blur, and you see it here. Let me just to show you that this, I just did toy examples, so let me just do one more example that's not so toy so that you can at least see it in action. Okay, so what I'm going to do is generate the matrix. So this is a 768 by 768 matrix. When I generate the blurring matrix, it's going to be 768 squared by 768 squared. So let me generate it. And I'm going to use 10 frames, like I added 10 frames to get my blurred image, 10 shakes of the head in some sense, if you like. And so I'm constructing that sparse matrix on this silly little laptop here. I didn't pre-compute anything, so it's doing it on the fly. All right, so when it creates it, it's going to be a sparse matrix, and it'll have a certain number of non-zeros in the matrix, of course. So now I'll try to show you what the number of non-zeros are in here. It'll finish.
Just a question.
Yes.
Does the detector timestamp all the detections?
Yeah, so it all comes out in list mode, right? So you get a list mode that you can read in. And I'll mention a little bit more about this. Okay,
so it's like many rapid frames.
Yes, exactly.
High resolution. Okay.
That's right. That's right. So here's the matrix. Again, it's 590,000 by 590,000 with like 19 million unknowns in it. And so let's see. I don't know. I guess that's the truth. Let me show you what the blurred image looks like. Again, the image shakes, right? And I keep shaking it back and forth. And I shook it randomly, actually, so forward and backward in random sort of sequence. And then let me just run our method, this Hyper method on it. And it's running, again, real time on this, really, it's a silly little laptop, this thing. It's just showing you the iterations as it goes. And I think it just takes a few iterations, and it computes a pretty good solution, actually, in this particular case. Now, again, this is something that is, again, a contrived example. I'm assuming I know all of the position information exactly. So I know the matrix A exactly, but I have noise in the right-hand side data. But in that case, I do quite good. Okay, so let me come back to here and say a little bit something about the realistic situation. Now, that was a 2D problem. And the problems really are 3D, and so they're much larger than this little 2D thing that I did. I can't show it real time in 3D. In addition, as I said, we're going to collect position information at 20 positions per second. And I said that they're in the machine for 20 to 30 minutes, which means I have 24,000 to 36,000 positions, which means I would have to sum up 24 to 36,000 of these matrices if I really wanted to model it exactly. And that's not really possible because the sparsity of that may grow quite dramatically, and not in addition to doing all this stuff. So what we do is we try to say each of these black marks is a single tick mark of a position of the head. And you can see that for a period of time, the patient is not moving very much, right? They're pretty steady. And then they got an itch. And when they scratched their itch, their head moved. And then they said, and the technician said, "Don't move." And so they stayed again. But then they start to get really impatient towards the end because they've been in there a long time. And so what we tried to do is figure out, okay, this is 3D motion, right? So it's 3D quaternion. We tried to gel that down into a single one-dimensional measure and say, this is constant here, this is constant, and so forth. And you might say, well, it's not really constant in these bins, but that's what we did. And then so instead of summing up 36,000 of these things, we'll sum up 1, assume a constant motion in here, 2, 3, 4, 5, 6, something like that. If you want to do more, you can say, well, let's put in some more lines in here and sum up some more. Okay, so that's what we're doing. And we built a tool and wrote this code. You say, you use Java to do this? Yeah, we use Java to do this. And we made this, I don't know if you know ImageJ, it's a tool that the people in radiology like. So we tried to build them a tool that they could use. And so we wrote this code in Java, partly because my student Piotr really wanted to do this, and so I let him do it. And he made this nice little GUI and gave it to the people in radiology, and they started using it, and they started generating clinical results. So that was pretty cool. All right. I'm running out of time, so let me go a little bit fast here. I want to talk a little bit about nonlinear inverse problems. And this is one slide on nonlinear inverse problems. So the problems, you can extend some of the ideas from linear problems, but the analysis is much harder. You can't take an SVD, for example. You might say, well, okay, let me take an SVD of the Jacobian or something, but the analysis doesn't translate so easily. But we can think of the basic ideas. So this used to be A times X. So let me add some Tikhonov regularization like ideas to it. I could do that. I can use iterative regularization. So I'll just use it, try to do this thing and do iterative regularization on it. And I can use any sort of Gauss-Newton type method, maybe Levenberg-Marquardt, and so forth and so on, right? So use your favorite iterative solver on some of these things. And then stop the iteration when you think it's a good solution. Okay, so let me come to this breast imaging application because I think this is a very nice application. Again, we're going to do 3D reconstructions from 2D projections. I sort of glossed over this. If those of you know computer tomography, you might say, well, why don't you just use CT rather than this limited angle thing? You'll get more data and get better pictures. But then you have to radiate the patient a lot more. And to use CT, typically the patient has to lay down on a table with a hole in it to get the full angle data. And it's difficult for some mobility challenged people. So tomosynthesis is really a nice model. Now, so this is a heavy end math, but the basic model is this. These are the projected images. and you have some integrals in here. The thing that you're looking for is this mu in here, and everything else you're going to assume is basically known. So you know some this rho thing and all this sort of stuff. And so, okay, that looks hard. So, so instead of using integrals, let's discretize it. So we'll replace the integrals by summations. And so I get these summations out. And anytime I see a summation times some discrete stuff, I'm thinking matrix vector or matrix multiplication. And that's what it turns out to be. So I get this, this problem that looks something like this. For each projection image, I have a matrix here. You can think of it as a radon transform, or we call it a ray trace matrix, times this m, which is attenuation coefficients in each voxel. And then we get, if we put them all together, we get something that looks like this. Now, it turns out that I sort of glossed over this. I'm summing over a whole bunch of energy levels. So it turns out that when you have this X-ray source, it emits X-rays. And typically what you do is you say, okay, well, what's the energy of the X-ray? What keV is it? Well, it turns out that actually it's a spectrum of keV that come out. And so what can you do with that? Well, you can just assume that there's only one average sort of X-ray energy that comes out. And if you do, then this problem can be reduced, this sort of nonlinear problem can be reduced down to a linear inverse problem. And you can solve it very, very quickly. On the other hand, in the limited angle tomography, you're missing a lot of information because you've only gotten a limited set of angles of data. So what we wanted to do was to not do that. We wanted to exploit the fact that, that there's a wide variety of spectrums coming out of here. So we tried to do that problem, and the problem becomes nonlinear. And so, so what we did is we solved it using basically a maximum likelihood type approach. We're using a Poisson model for the likelihood function because this is something that makes sense in X-ray imaging. You're counting photons in some sense that hit the detector. And so you get this likelihood function, and you want to compute this solution here from this. Okay, I know I'm going fast, but let me just get to the meat of it. So we used a variety of different iterative methods on this thing. And just used iterative regularization, tried to stop it when we thought a good solution was there. I'm going to show three different sets of examples. One is, this is a made-up software data. These are the projection images. I don't know if what they look like to you, but they look like a mess. If I look at the truth data, this would be the top part here. You see, we put this little blob in here, and we said, well, so can we find it? Can we find it? So this is the linear reconstruction, assuming that the energies come out at a single X-ray, and it's hard to see it. You might see it in there, but it's not so good. If I use our scheme, either a gradient descent or a Newton method, both of them do quite a bit better. Now, gradient descent, we might have run more iterations and gotten as good as Newton, but we decided to stop at 20 iterations there. So that's this made-up problem. I made that up and did it. I didn't make it up. Julianne made it up. This is a problem that actually is real data from the machine. It's a hardware phantom, so it's an object they put in the machine, and they took data from it and did the reconstructions. And I'm just showing you a small portion of it. This is the reconstruction that the machine gave, and this is the reconstruction from our algorithm. You say, well, I don't know which one you like better. But let me just tell you that these black streaks above and below these things are not supposed to be there. Those are called beam hardening artifacts. And that comes from the limited angle stuff that we're not seeing as much in ours. Now, the amazing thing about this actually is that this is for real data from the machine. And the model, the function that you have to write down for this thing depends on the parameters of the machine, right? So what's the distance from the X-ray source to the detector? What angle is the detector? Is it perfectly flat, or does it move each time the detector or the source moves? All of that stuff is proprietary, and we can't get that information from the vendor. So we had to guess at it. We reverse engineered it in some sense. And so the fact that we can do this as well as this without knowing exactly what the machine is doing, and they know exactly what it's doing, I think is quite good. And then, again, let me show you this is a real patient data. These are the projections that we took. Again, you can't really see much in the images. These are each individual projections, what a mammography would look like. And then here I'm going to show the mammography, and here I'm going to show the reconstruction of each individual slice. And you can see, you start to see more and more detail. And again, you see this, as I showed in the beginning, this calcification starts to come up, which you would never see in one of these projections. So that's quite nice there. All right, so let me just close. I think these large-scale inverse problems are, of course, quite challenging. I think in medical imaging, one of the issues is that they don't want to use supercomputers, right? I mean, necessarily. They want to have solvers that work well on commodity architectures, something that they can put in their lab. We've tried to write as much software as we can that people can use. And so this is some of the stuff some of the software that I used in the talk today. Piotr's Java software he has on this site here. And we're writing now this OpenCL and CUDA stuff for some of this, the tomosynthesis stuff as well. And hopefully that will be done soon. All right, thanks very much.
Thank you very much, Jim. We have time for questions. Sasha?
I'm very curious. You had a slide, 2 slides back, where you had 2 different methods. One was in Newton, and one wasn't in Newton. Just one.
Yeah, I know what you're talking about.
Yes.
Yeah.
So I was curious. The algorithm, the hybrid. Are you able to build the part where you regularize and pick the regularization parameter on top of any optimization method, and you're comparing that for 2 different optimizations?
We're not using that hybrid method here at all.
Oh.
So you might think about doing it. So in Newton, I have this, I have this Hessian solve that I have to do in there. So I might think about trying to use it for the Hessian solve, but we didn't do that there. Or if I were using a Gauss-Newton method, I might think about, LDOT has done this before, trying to use something like that for solving the Jacobian system in some sense. And so you did this many years ago in some sense, the hybrid methods like that. So, but we didn't do that here.
And then what was?
Regularization, we just did iterative regularization, so we just tried to stop it when we thought the solution was good.
Okay.
And how do I know when to stop? I don't. I just we're just playing right now, actually. So this actually is work in progress, and it's more playing right now than it is anything useful that we can pass along to anybody.
How does preconditioning mess with iterative regularization? Because I imagine if the precondition is too good, it's going to screw you over.
Yeah, it'll screw you over, very badly, right? So if you go back to the linear problems, right? So I don't have to come back to a linear problem, right? So, or maybe I can use a chalkboard or a whiteboard or something, right? So maybe I should use a whiteboard. The problem is I have AX plus noise is equal to B. Okay, so now I ask you, how do you want to precondition? Left or right preconditioning? No, it's a good question, right? If I do right preconditioning, so that means I'm going to hit the matrix on the right, if you do left preconditioning, I might hit it with an M inverse B equals M inverse X plus M inverse noise. Okay, so the problem with that, and it might work well, the problem with this is that usually the algorithms that you build are built on statistical models of your data. So if this were normally distributed Gaussian white noise, then what is this, right? So you have to incorporate that maybe into the covariance matrix. So your metric then may change. You can do right preconditioning, so I can have B is equal to A M inverse M X plus noise, and that won't mess with my noise statistics. So I could do something like that. And Uri and I were talking about this earlier. This is a method that these guys have used for a long time to incorporate regularization type things. So I could use a Laplacian in here to say penalize my Laplacian type, do like so to have a smooth derivative in my solution or something like that. So in that case, preconditioning isn't used necessarily to accelerate convergence, but to guide what kind of solution that I want to get.
So what about the smoothness of, so, you know, I mean, at least in your simple examples, you had something that it's, you know, infinitely differentiable. So what if I had a highly discontinuous image that I want to reconstruct? What would happen in those situations?
Well, if you're going to use Tikhonov regularization, it's going to smooth the edges. So if you have a lot of edges in your image, it's going to make them smooth in some sense. So
will not have any jumps around the discontinuities?
No, you can try to incorporate maybe in a preconditioner where you say try to identify in some sense the edges within these things. This is John Bardsley's done some work on this recently. You could use total variation or L1 minimization type things that preserve the edges. These are techniques actually that could work quite well in those cases. But in general, if you have a lot of edges, yeah, Tikhonov type regularization is going to smooth them out.
I know for the error, it's very convenient to assume white noise.
Yes.
I'm wondering if anyone has used color noise in place of white noise, or if it's still the convention to use white noise.
So if you have colored noise, you can pre-whiten the data, right? And then you need to know the covariance matrix of your noise. The other issue is to decide whether it really is Gaussian, normally distributed stuff, or if it has Poisson characteristics to the data, which it could, right? Because your data collects, if you think about a camera, it's collecting photon counts. And there's going to be background radiation, so there's going to be background photons that you're getting in there, right? And those background photons are counting noise. And that counting noise should be modeled as a Poisson statistics. Now, you can just say, okay, the central limit theorem just allows me to approximate everything by a Gaussian, so I'll just do a Gaussian. So that's okay. So yeah, but if you use a Poisson model or something like that, you can use a different likelihood function rather than least squares.
Yes. All right, so let's thank Jim again for a good talk.